recording. Okay, now if we take a look on the last discussion, we have the triple integral. Okay. And what we have here is we may have a chance for changing the last double integral here into a polar So you can convert this into a polar in the triple integrals as well. Okay. But the way you are doing it is the same as we did in the polar coordinates. So we need to evaluate the inside integrations, and then after that we can convert to polar like in the 15.3 as usual. Okay, let me move to the next subject, that is the how to change the order of the integrations. Okay. So changing the order integration is basically if we have integrations, functions, uh, let's say dv and e. Okay. Let's say we have the dv we can write as dx dy dz, right? You can write dy dx dz, and it's up to you, up your preference, which way you are more going to be more likely used in the solutions. But what we have in this subject is how do we change? Okay, how do we change the order of integrations? I think for double integral, we could have easily observe and analyze through just sketching the two dimensions. Okay, and we could see how uh, the region can be observed, and we can easily substitute dy dx becomes dx dy, right? For double integral. But for this triple integral, there is a little bit complex situation, okay? Because we are going to observe the three-dimension space, right? So, for example, if you would like to express, okay, let's say I will just write directly the example. So let's say we have this the order as dz, dy, and dx, right? And what we have, or what we are going to achieve, we need to exchange this order by dx, dz, dy, and the second dy, dx, and dz. Okay. Now let's just write for the general part. You could write this as triple integral and then dv. Okay, and then we could start with mentioning e as the based on what we have here. So first is 0 to 1 for x, and then 0 to x squared, okay, for y, and then for z we have from 0 z and then y. Okay. Okay, from this descriptions, okay, I think we could easily draw the xy, right? We could have the x squared, and we have the x like that, right? For xy plane, and for the yz and xz, according to what we have here, we could also, I think, easily transfer into two dimension projections. But let's say we are going to observe the three dimensions. Let's say we are going to observe this e. Okay, so this is what we have. Okay, so we start from, let's say, the x-axis. Okay? The x-axis from 0 to 1. Okay, so this is the observations path that we are going to look at. And then we have for y we have 0 and x squared. So 0 here, x squared is this one, right? So we could also see up until x equal 1 is here. Let me just draw. Okay. Now we have this xy plane. I think it could be drawn easily. But the difficult part, and you need to have good imagination in your mind, is if we are going to put this z. Okay? So z equal y. Okay, let me draw the z equal y in yz plane first. So this is a z equal y. Okay, that is z equal y, and imagine that z equal y is like having a plane that is goes by the slope of according to z equal y. So you have if you could imagine that this is the plane, okay, the plane that you are put in the system, that is will be the plane, and then the plane will be crossing all the things in the in the solid E that you have here, right? Now if you have, then the next thing is all the lines should be interconnected each other. Okay, so first, if you look on this x squared, okay, because z is equal to y, we could also write that z also equal x squared. Okay, which we are going to have in this one. And according to all the intersections that we might have, this will project it through here. So this will be z equal x squared at the z equal y, right? Okay. So that's why we have this solids. Okay. I hope you could follow the steps that I've shown you. Okay. Now, the thing is how to change the order of integrations. So how to change is basically first we need to translate. Okay, we need to translate the solid E into 2D projection. So this 3 dimensions shape we need to project to 2 dimensions. Okay, so we need to project to xz plane, yz plane, and xy plane. Okay, so we need to project through here. Okay, this plane, and xy plane. Okay, so I believe we could do that. Let me just go put all the 3 projections. Okay, so first, the easy one is xy plane. We have d1. Okay, so we have x squared from x equals 0 to x equals 1, right? And then d2 is yz plane. We could have this, right? So that's the projections, the triangle. So z equal y, and then from y equal 0 to equal 1, and then xz plane. So xz plane, if you see, okay, this line here, x equal 1, is from here, from this line. So we could project this through here, right? So we could say that this will be our projections, and this projected through this. That's how we project the all these 3 different planes: xy plane, yz plane, and xz plane. Okay, so the next thing is we could write down all the possibility. If, for example, we let me maybe write here. Maybe erase first, erase first. Maybe it goes to a little bit to the right. Then we could write from D1 is basically, this is, we could say this is the original one. Okay, and then we could write, let me write it different color. We could write and making y as our outside integrations, right? And then we could have from x should be from 0, right? Or rather, for x, if we take this 0, 1 as our y, then x will be start from this curve, right? Until x equal 1, okay? So we could say that this will be square root of y, x, and then 1. That's for D1. And let's say for D2, this is start from y and then z. Okay, let's say we start from z, okay, as our outside integrations. So z start from 0 to 1, okay? And then y will start from this line here. So we start from z equal y, or now we have in terms of z. Okay. And then the last one is the third one. Start from x, and then z and x squared. Okay, this is based on the information given. Okay, now we have, let's say, from 0 to 1 for z, this one. So x start from the curve, right? Start from the curve, square root of c to x equal 1. Okay, now based on our variations in D1, D2, and D3, we could have several steps to make out for the one that we are going to achieve. So first is we are going to achieve dx, dz, dy. This could be written as, let me just write all the dx, dz, dy. Okay. Now the outside will be y. So y outside will start from 0 to 1. And then dz, will be from 0 to y. Okay. And then dx. Dx will be going to have square root of y and then 1. Okay, now the last one that we need to achieve is dy, dx, and dz. So dz is 0, 1. Let me write first. So dz is 0, 1. And then dx is going to have square root of z to 1 from here. I think that's the best way. Square root of z to 1. And then dy. So dy will be, should be related to x. Should be z and x squared. So you could write down this squared, or maybe z to the x squared. Okay, you could also imagine an the main point here, uh, for this case, and this case, the main essentials is we are going to imagine the upper surface and the lower surface of the E. Okay. So if we have this, okay, if we could imagine, uh, let's say the z and x squared, okay, for y. So y is from z. Y from z is, I erase first to make it clear. So y equals z is in the side here, and then y equal x squared is actually here. But we could also look on this one. Okay. So we could say that this could be our lower, right? It could be our lower surface, and this will be upper surface. So upper, lower. Okay, we could see that. And for the x squared of y is this. Okay, let me write x squared of y until 1, until x equal 1, up until here. So this will be upper and lower. Okay. So this is upper, this is lower. Okay, you could also see from those points. Okay, and the other thing that I think what you are going to need is basically you could see from this outside integrals. Okay, so it should be like telling a story. Okay, so dy, okay, this second part should be about function of y. Okay, should be related to this, and the last one, it could be related to z. It could be related to y. Same thing here. X should be related to function of z, as you see from the square root of z, and y should be related to x and or related to z. Okay, so it could be a function of two variables. Okay? Well, function of single variable also possible, like the first one here. You don't have function of variables in the integration here. It depends on the situation, on the cross sections that you are going to observe. Sometimes it's a little bit tedious because you need to imagine a lot of things. Imagine at least making these three projections. Sorry, making these three projections through all planes. But as long as you are keep consistent doing these projections, I think you will see what is the endpoints for each integral. Okay, maybe in the future we'll put some videos for another example on how we can apply the this change of integrations for the triple integral. Okay, maybe another practice. But for now, let's just uh, looking at this example. Okay. Okay. There's no questions. Is there any questions from you? Okay. Right. I think we can move on. we could move to another sections, which is the application of triple integral. Okay, so a little bit of applications, okay, for triple integrals. Is if we could define a volume for solid A as if we have triple integral and we already defined the solid E as in the um, in the triple integration itself, then we could just triple integrate the constant, and then this will be defined as a volume. Okay. So if we could start with, let's say, constant 1, and we could, let's say, start to work on the inside integral, and we say that this is having a lower and upper surface for the function of two variables, we could write this, right? We could differentiate with this, and then integrate double integral. This will be u2 xy minus u1 xy, and then dA. And then we know that this is represent, and what we have here is actually, if you remember this double integral and you have this subtractions, this means that the volume that lies between z equal u2 xy and z equal u1 xy, right? Okay. So you could apply this this property when you are having different boundary for different well, if you could have like two different functions for function of two variables, you could take the subtractions and make it into our triple integrations for finding the volume. Okay. If my words seems complicated, let me just see the example. Okay. Example. Find volume of tetrahedron T bounded by, first is the planes x plus 2y plus z equal to x equal 2y, x equals 0, and then z equals 0. Okay, so you can notice that we have line x equal to y, x equals 0, where z equals 0, which means at the xy plane we have some line that is crossing, and I think it could be easily drawn for this plane. We could find the intersections. Okay, find the intersections for each of the axes. So you could imagine to find intercept z, you could take x0 and y0, so z equal 2, right? And you could do the same thing for the other part. Okay, and then you could draw the line. You could draw all the line here. And what you could see is we will have I think this one. Yeah, so we could have this. Okay, it should be the plane is, according to what we have here, it should be going through here, right? The plane. But since we have this x equal 2y or y equal half x, then the tetrahedron is cut. Okay, cut at this point, So this will be the plane for x equal to y from here, right? That is the plane. And then cut from here. So that's the tetrahedron, creating the tetrahedron. Let me just erase first. And then another thing that is important is we look at on the D here. Okay, now we have this is from the x equal to y, right? X equal to y. We could write in terms of y, and then we could also write the line, this one. So this is practically when z is equal 0. So we could say x plus 2y is equal to, or we could take it into y. So it will be 1 minus half x, right? Now, the next thing is we could take the volume as integrations. Let's just write triple integral dv. Okay. And for t, this t region, we could say, and we could write okay, let's say we have dz, dy, dx. Okay. So x, we will going to start with, if we could see the xy for the d, so we could see from this d region. So we could start from 0 to 1, right? So 0, 1 for x. And for y, it should be having a function of x. So we could start from this side here until this side, the upper one, right? So we could start from x over 2 until 1 minus x over 2. Okay. Now z, we could start z from 0, from the very bottom. So 0, and start z as a function of two variables. Okay. So let z equals 0, or let z is from z equals 0. So from z equals 0. So from z equals 0. So this is z equals 0 up until here, right? All the plane here. So we could say that z is 2 minus x minus 2y. That will be our z, our function of two variables. So we could write down here 2 minus x minus 2y. Now we could also going to evaluate dz becomes z, and this becomes then dy dx. Okay. And I think this is just a normal double integral. We could integrate through y, right? So we could have 2y minus xy minus 2y squared, right? And then input the x over 2 and minus 1 minus x over 2 going to dy, and then later on differentiate, integrate with respect to x. If you calculate, this will equal to 1 over 3. Okay. Now there is another application that is related to the lamina and mass, but since we are skipping the 15.4, so we don't need to calculate the application for the lamina. Okay. So that's it, the triple integral. Okay, so we finished the triple integral. Yeah, maybe could you could have more review and explanations probably later on. But if you have any questions, or do you need some practice? Check the. Okay, maybe a little bit practice. Maybe giving you more example. First is evaluation of triple integral with certain region of t. Okay. And let me give you the examples. Let's say the example, we have triple integral y squared dphi. Okay. And t is solid. Tetrahedron. It's similar to what we have before with vertices 0, 0, 0, 1, 2, 2, 0, 0, 0, 2, 0, and 0, 0, 2. So we need to evaluate this triple integral. Okay. So at least, first thing we can do is perhaps we could just draw all these vertices and we could draw the tetrahedron, right? So let me just draw for you here. So start from 0, 0, 0, what's this one, I think? And then all the cross points will have the units too, right? So this will be our tetrahedron. Okay. And finish the tetrahedron, and then I think we can agree that this tetrahedron is x plus y plus z equal to, right? Because all the cross section is having units. Okay, I think we could start to define our dphi, our dphi. So dphi we could define as because I think I will just take z as a function of two variables, so I will take z in the inside, right? Inside, and the outside can be dy dx or dx dy. But let's say dy dx to make it more um, uh, consistent, like in order, like x is our, just take it as our default to make it easy. So x, we could start from define the interval of x. So we could write t x y z, and then start with x from 0 to 2, and then we write this a little bit maybe here. And then for y, it should be a function of x. Should be a function of x, but let's see. So if this is x from 0 to 2, this is x, then this will be y, right? This one. So this is x going from here, then y is from 0, right? From 0 up until this line here. Okay. And this line is x plus 2 equal y. Equal to, sorry, x plus y equal to. And y is 2 minus x. So we could write down that y is start from 0 to 2 minus x. Okay. Okay. And then z should be a function of two variables and start from z equals 0, right? From 0, 0, 0, this plane. So from the xy plane until the our planes x plus y plus z equal 2, or we could write z as 2 minus x minus y, right? So z will be from 0 to 2 minus x minus 1. Okay, I hope this can be understood. And then we could write down the triple integrations from 0 to 2, from 0 to 2 minus x, from 0 to 2 minus x minus y, and then y squared dz dy dx. Okay, now start with just taking dz into z. So we could have two minus x minus y multiply with y squared dy dx. We could work on this. And we could integral with respect to dy. It's become 2 over 3 y cubed minus x y cubed, or maybe we could just make into y squared is 2 minus x, so y cubed over 3, 2 minus x, and then y 4 over 4. Okay. So this will be from 0 to 2 minus x, still we have 0 to dx. And then later on, we could have oh wait. We need to we need to put in the 2 minus x first. Okay, we need to put in 2 minus x. So 2 minus x cubed, so 2 minus x 4 over 3 minus 2 minus x 4 over 4. And put 0, it's all 0, so this will be still having integral, and this will be 1 over 3 minus 1 over 4, right? So we could have 1 over 12, 2 minus x with power of 4 dx. Now still doing integrations. So 2 minus x with power of 4, it's become 2 minus x with 5. But we have 5 and minus, right? And then still we need to multiply with 1 over 12 from 0 to 2. So this will be negative 1 over 6c. And the inside will be 2 minus x. 2 minus 2 is 0. Minus 0 is 2 with power of 5, 32. Right? So positive 32 over 60. Or this will be divided by 4 is 8. And I think still the calculation is not too difficult, but I think as long as you get corrected from this one, I think should be okay. Okay, now another example. Okay, another example. I think one more example, and we can move to next sections, which is the 15.7. 15.7, the cylinder coordinates. Okay, I hope you can take some important notes from today's lecture. Do you have any questions before we continue? Do you have questions? Anything that you miss out that I need to maybe explain again? Is there anything that you need to review? No, I think we could continue. I will give you example, and you can try for a while. Okay, try for a few minutes. Uh, Find the volume of the given solid. So the solid first is the solid enclosed by paraboloids. Y equal x squared plus z squared, and y equal 8 minus x squared minus z squared. You could try for a few minutes. Give you maybe 2 minutes, 3 minutes. You can check. You could check, and before you start, uh, you could look at these two paraboloids. They are exactly similar, but the other one is the opposite, right? So please, I'm giving you maybe a couple minutes to try. Okay. Anyone find the answer? Okay, now first, if you could imagine what is the shape uh, of these two paraboloids, if we could draw at least just to show uh, how the shape is going to be look like. So first is the one that is just an ordinary paraboloid, which is this one, right? Oh, I need to draw a little bit longer. Sorry. Now, the other paraboloids will be should be 8, and then it should be goes here, right? Too long. Maybe it's a little bit short. Maybe here. That will be the other paraboloid. If you could imagine how it looks like for the 8 minus x squared minus z squared. Now, the idea here is these two paraboloids will have a cross section. They will have a cross section here. Probably here. That will be the cross section. We could see easily the cross section from if we equaling these two paraboloids. So x squared plus z squared equal 8 minus x squared minus z squared. Okay, we could solve this. It becomes, and we could simplify become x squared plus z squared 4. So we have a circle that is equal to 4. For the radius is 2. Radius is 2. Okay. So projections E on xc plane, right? Xc plane. So first we could write down the E. If you would like to write completely, we could write E, and then we could say that this will be the upper and lower surface for this y. Okay? So 8 minus x squared minus z squared, right? So this will be the upper, this will be the lower, right? Okay. And then the other thing is we could have the circle that is having radius 2 for on the axis plane. Okay. Now within these two uh, conjectures, we could write the uh, the d as our d, like in a double integral. So xc, we could just write x squared plus c squared. Okay. Okay. Now then, we could just take the polar coordinates. Okay. So convert to polar. And let me just write the idea here, E dv, and this will be d, and the inside integrations will be start from x squared plus c squared, and then this will be 8 minus x squared minus c squared. This will be dy, and then this is, let's say, dA. Sorry, should be that. Okay. The first one we could just solve and make it into our equations. So dA. And now for d, we could just take the polar. So convert to polar. So radius is from 0 to, and for theta is from 0 to 2 pi. So we could just describe in polar. 0 2 pi 0 2, and this will be 8 minus 2r squared, right? And this will be r, d theta. And solve as usual. I think you can just solve it and you can find the answer. Okay. I think after you get all the polars, you get the equations at the integrations, the calculation will be not very difficult. Should be. Okay, it should be not very difficult. And the difficulty is to set up the integral itself. That's the if you would like to observe the difficulty, that will be the difficult part. Okay, any questions? Okay. Any questions? Anyway, what do you think about the quiz? In the quizzes, what do you think about the quiz? Anyone maybe have a comment? Is it too difficult? The time is too short, or any comments you might have? Okay. And I think my suggestions for saving the times, you could just, if you want to like summarize, if you want to make a summary of your notes, make the summary. I think that will be very good. So you can have maybe one A4 or two A4. Maybe one A4 is for which chapter you would like to write on that paper, and the other paper maybe from chapter, maybe another chapter. And I think that will be easier for you if you want to take the notes when you have the exam. So the final exam, and then it will be open notes, okay? Because I wouldn't be able to supervise all of you, so I will just take it open notes. With some schedule, some sort of time, maybe 2 to 3 hours. And when you are doing the final exam, you are also need to open your camera. If we are using the WebEx, we need to open the camera. But sometimes if the WebEx is not working, because sometimes it's I have some trouble with WebEx. Sometimes they are not connecting, although my connection is quite fast. So sometimes it has trouble, so we might change to other platform just to let you open the camera and make sure that you are working by yourself. Okay. You could prepare notes, calculator. I think that should be better. If you want to prepare books, also fine, but I think it will be difficult because the time limit. But it's up to you. It's up to you. Okay. Anyway, if there's no question, then we could just move on. Okay, we could just move on to the next chapter. Not chapter, but rather the next sections of chapter 15. It's 15.7. So we are, I think, another 3 meetings or 4 meetings. We will finish chapter 15. I will just having some review and some practice afterwards, and then after that, just prepare for the final exam. Okay. Final exam probably in the second week of June, or maybe before 10. Okay, before 10 June. So you could prepare your schedule. Okay, from now. If you want to have like maybe having a vacations, going somewhere, maybe going to your home if you are outside of Taipei, you could prepare. Maybe you could prepare after June of 10. Okay. Or if the connection, because we are having online exam, so I think it doesn't matter if you just go. I think. Okay. All right. I think we can just continue. Okay. Let me just continue. Now is 15.7. Okay, 15.7. So it's triple integrals in cylindrical coordinates. Oh, by the way, I just uploaded the exercise for additional videos. I will later announce in the Moodle also. Okay. So what is cylindrical coordinates? First, we need to understand the coordinate itself, okay, before we go to the integrals. Okay. We could start with just looking at the polar system. You could just see at the polar system that the polar that we could have some relations with x, like, and y, and also x squared plus y squared is r squared. Also, tangent theta is y over x. Okay, for all these four, we simply convert uh, the polar. Okay, now the cylindrical coordinates. Okay, in short, okay, if I would like to make some definition, uh, it's similar to polar. So it's polar, but plus another axis c. Okay, for example, another axis. So you'll have a polar in one aspect, which is the maybe one plane that is polar, but you will have another aspect that is the height. Okay? So z is height. So that's the coordinate of the cylindrical. Okay? So let me just give you uh, a way to see what is this coordinate. Okay. So if we have, okay, let's say we are going to have uh, maybe we start with the radius and theta is a polar, right? It's a polar system. Okay. If we add another axis, which the one I told you that is z, the height, this will be, we say, if we have these three coordinates r, theta, and z, this will be, we call the cylindrical coordinate system. And to convert is just convert the polar as usual. Okay, because z is just z, it's nothing related to the polar. So z is just z. Okay, now if you would like to imagine, okay, so if we have these three variables, r, theta, and z, we could see what it would be like to if, for example, the r, if the r is constant and the other is variable, and when the theta is constant and z is constant, what will happen to the other variable? So we could also observe. Okay, so if r is a constant, I think it's easy to say that we could recall what we have done in the previous samples in chapter 12, right? We have the cylinder, right? So we have, like, for example, x squared plus y squared is 4 in 3 dimensions. This will be going to have a cylinder, right? A perfect cylinder with the radius is a constant. Okay, I think it's easy to imagine. Okay, now if we have the theta is a constant, which means that the line is not going anywhere for some reason. This is just theta, it's a constant, it's just stay as it is. Then you have a plane that is vertically going upwards and downwards, right? And for z equal constant, you're not going anywhere, so you have a horizontal plane. Okay. And now after we deal with this coordinate system, the cylindrical coordinate system, and what it looks like when we are going to observe when they have each of variable constant, now we have the triple integral. And basically what we have here is actually similar to what we have in the polar system in the double integral. It was similar, but in the triple integral you just need to add another variable z. Okay. Now suppose that E is our solid. Okay, we have our solid. Now if we imagine in a cylinder, if we could imagine that z is a function of two variables, let's say E is if we could imagine this as xyz, let's say this xy is also, we could say d, then the function of two variables is our lower and upper surface, right? If you remember what we have in the last section of triple integral. And since d is in a polar system, we could transform this into r and theta. Okay, so sorry, it should be r theta. And let's say the theta is from alpha to beta. And R will be a polar equations. Okay. And then let me just copy all this. Let me just copy all this and move to the next page. And then from the equation we have before, we could start with describing the integrations as triple integral. And then later we need to convert this dA to the polar. Okay, now convert d to polar. So we have this will be equal to the polar start from alpha to beta for the angle, and then this will be the polar equations, function of theta, and inside one this will be r plus theta, r sine theta. Okay, and then this will be f r cos theta, r sine theta, and c is still z. And the integrations will be still we have need to multiply with r, and then dz, dr, d theta. So this is a formula for triple integration in cylindrical coordinate. Now, if we would like to see in a more convenient way what we have in the cylindrical, if we cut the cylinder, we could also see these observations, and we could also consider these small pieces. Okay? If you calculate the volume, as a volume in a rectangle, we could compute r, right? Is r d theta, dz dr, or we could arrange into dz dr d theta. So the way you are writing these polars should be still similar. So dr d theta should be at the very end. And what you need is to add is the in between r and d dr. Okay. Okay, any questions? Okay, if not, then maybe example, one or two example. I think this should be important. Okay. Okay. I will give you example. I think we can um, write the example in the next section. Okay. Evaluate so E is the solid that lies under paraboloid z equal 4 minus x squared minus y squared and above xy plane or z equals 0, right? Z equals 0. Okay, maybe you could think on how to solve this. But it's actually, I think there's not really a special case, right? The cylindrical, if you think clearly, it's just usual triple integrals. And then at the end, you just convert the double integral, the last double integral with polar, right? But what's important in the cylindrical coordinates, because you can convert and before where we learn the triple integrals, and when we deal with the polar, we convert the polar later on after we finish doing the integral inside, right? But now, because we have some conversions directly, then we can, I think, solve faster and just convert into the cylindrical, right? So we could convert directly this z. We could see that this is 4 minus r squared, right? We could clearly see. And if we look at in the projections, when you have z equals 0, so you will have x squared plus y squared equal 4. So you will know that the radius is from 0 to 2. Okay, and there's nothing in between the angle. So the angle is from theta to 2 pi. And I think we can just directly evaluate. Or if you would like to draw the curve and see what this looks like, we could just draw easily. Okay. And I don't think we need to draw, because I think 4 minus x squared minus y squared, it can be easily visualized in our mind, right? So first, we could write r, theta, and z. Okay, that's our interval for all three variables for the cylindrical coordinates. Then we could have e x squared dv. Now we have the theta is 0, 2 pi, and then r is 0, 2, and then z is 0, 4 minus r squared. And x become r cos theta squared, and then r dz dr d theta. Okay. Start from inside. Could start from r cubed cos squared theta, okay, and then dz, and integrate. This will be multiplied with 4 minus r squared, r cubed cosine squared theta, right? Could just write down and dr d theta, right? And then look closely. I think we could separate. So if we deal with this, we could write or we could just write as like this. And you see that perfectly we have this is a theta, this is r. So we could separate dr and d theta. So we could write 0, 2 pi. This will be cos squared theta d theta. And the other one 0, 2 for r cubed minus r5 dr. And I think we can follow just normal integrations. So this cos squared, we could have 1 plus cos 2 theta divided by 2. Right? So we could say half, and then this will become theta. This will become sine 2 theta over 2 from 0 to 2 pi. And the other one, this will be r4, r6 over 6 from 0 to 2. And this will be 2 pi, 0, sine will be 0. So 2 pi, so pi multiply with, so it will be 16 minus 32 divided by 3, right? So it will be 48, 16 over 3 pi. Okay, any questions? Okay, if you feel that you need to look on the picture as observations, we could see from this observation here. Okay, so if we start from z, it has some variation from 0, from z equals 0, so from this plane, and this goes up, and how the z goes up, it's based on the curve 4 minus r squared, right? This, right? Okay. And then for different in r, course, it's just from 0 to 2. There's no other obstacle. And then you rotate the angle, right? Rotate the angle from 0 to 2 pi. Okay? All right. Okay. Okay, I think, let me check. Okay, maybe give you another example. And we have maybe one more exercise or two. And then we could go to the triple integral in spherical coordinates. Okay, maybe before that, let me check. Okay, maybe giving you one example. Okay, example, evaluate. So you are given the triple integral. Okay, okay, please try for one. While you are doing so, maybe you can write down the question first. I will give you this QR code for this. I think there are some of you, I think not haven't scanned, right? Let me just give you again. So okay, so please evaluate first. Uh, I will stop the sharing for a while. I'm giving you the. Wait. I think we could see this the other screen first. Okay, we check first. Okay, I believe you'll have scanned the QR code. Stop the sharing and share again the notes. Okay, I think we can solve this. Okay, now first we could write down the E, the interval for each axis. And then Z is from, okay, now we have this E. Now if we would like to see, okay, the Z, okay, it's from the square root of x squared plus y squared up until 2, up until Z equal to. If we project to xy plane, okay, if we project this to xy plane, this will be having these equations for the projections, right? So if we would like to maybe looking at what it looks like, and I believe this will be very consistent if we could see from the second one. We have 4 minus x squared, or we have x squared plus y squared is, so it could be consistent, and we could draw the formulations or the sketching the upper and lower surface, and we see that this will be the lower, okay, lower surface. This would be the upper surface, right? And okay, we could then exchange to r, theta, and z. Okay, so we could exchange all with the terms in the polar, okay, and then we have then, based on our polar, this will be from 0 to 2 pi for the circle, and for the r is 0 to 2. For the z is from r to 2. R squared, r dr, sorry, dz dr d theta, dz dr d theta. And here's we could just take I think directly just write 2 pi, and this one is having z, right? Z is 2 minus r, okay, so, and then r cubed. So 2r cubed minus r4, we could integrate. So integrate 0 to 2r cubed minus r4 dr. Okay, and this will be r4 over 2, r5 over 5. So 2 pi from 0 to 2. So 16 over 2, 8, or 8 minus 32 over 5. 8 minus 32 over 5. So this will be equal to 16 over 5. Okay. Any questions? If not, I think we can move to next section. It's 15.8. 15.8. I would just maybe just go for introduction for 15.8, and we continue later next week. And probably having some exercise first for 15.7 and 15.8, and then 15.9. Okay. And then exercise and review. So probably 2 or 3 more class. That will be my goal. Okay. So finish at least to finish the chapters first, and then the rest of the class maybe having one or two will be about the review and how to prepare your final exam. Okay. Okay, I think we can move to 15.8. Yeah, I think we can move to 15.8. Any question from this one? Okay, anyone having confusion, or maybe you want to see some review what I've been talking about? We could go back to review the contents if you would like. But let me just go through 15.8. Okay. Okay, 15.8. This will be the spherical coordinates. So triple integral in spherical coordinates. First, we need to define what is spherical coordinates. Of course, spherical means the coordinate in a sphere. So you could just imagine a sphere, okay, and then let the sphere have uh, some variable to define its position, okay, in every positions in the sphere, right? So first thing we can do is perhaps we could just take this approach, okay, that when we have a sphere, when you have a sphere, uh, the sphere will have it has the radius, right? It has radius. The radius is rho, okay, and other two variables will be about the angle. The first one is angle on the theta here, and the second one is the psi around here. Okay, we could say that the radius rho is the distance of OP, right? And theta is the same angle as the cylindrical, right? And the psi is angle between z-axis, positive z-axis, and line segment OP. And we need to note that this will be the definition for the interval, and then so the radius should be positive, and the psi will be between 0 and 5. And then similar with the cylindrical coordinates, let's observe all the conditions when we have certain variable. Okay, we have certain variable as a constant, and we can see how the other variable will behave. And we could see from here, if our radius is a constant, of course we would have a perfect sphere. Okay, perfect sphere. it's like the chapter 12, the quadratic surface. You remember the ellipsoid, right? If we have a perfect x squared plus y squared plus z squared equal a constant a, this will be a sphere, right? And now if the angle in xy plane here, the theta, if it is a constant, we'll have a half plane, okay, half plane, right? And then if you have psi as a constant, okay, if it is a constant, you could say that you can rotate, okay, you could rotate from here, rotate, and it goes back to the original point. So if you rotate from 0 to pi over 2, you would have that way. If you rotate from pi over 2 to pi, you could have the other way around. And you have the another half cone. Okay. Now to convert the the rectangular to spherical, we need to have some sort of uh, equations and formulations through what we have here. Okay. Now first, let's imagine we have the xyz and we need to convert to here, okay, to rho, theta, and psi. Okay. Now first, I think the easy one that we can convert is z. Z we can convert through the triangle OPQ. Okay, so from triangle OPQ, Z is rho cosine sine. Okay, and from triangle OP and P prime. Okay, so from triangle OP P prime, we could have another triangle, which is we can define the R is rho sine sine. Okay. And from this r cosine theta for x and y r sine theta, we could just exchange r with this. Okay. So we could have x is rho sine psi cos theta and y is rho sine psi sine theta. Okay. And from the distance formula and the usual sphere formula that you have, we could also write down that the distance is equal to rho squared. So I believe through this, let me write another one. C is rho cosine sine. So if we have convert all x, y, z into rho, psi, and theta. So we are using these conversions to convert the rectangular to spherical. All right. I think I will just stop until here for the introduction for the spherical coordinates. I will continue next Tuesday for the triple integrals in this, for the integrations for the spherical coordinates. The next thing we are going to have is feedback. Okay, feedback. Okay, and while we are doing that, maybe I will just let you write this for a while. Okay. Okay, any questions so far? Any questions? Okay, I think I will stop the sharing and give you the screen. And the screen. Okay. Okay. I think we can start the feedback. Let me go check. So please join the feedback through this QR code. Okay. Okay, please join. I will wait for a few minutes for you to join all the for the feedback. If you think you need to have some review or questions, let me know. Okay. In another week, I still will keep doing the additional video for some practice, so that you can, if you would like to know more on practice, you can follow the additional videos. If you still maybe having difficulty watching the additional videos, let me know. Okay, maybe which part that you feel still confused. Right? Okay, I think we could start. Right? We could start. Okay, use your name. I think student ID would be better. I will wait. Is there anyone join? It's just 8 students. Okay, please write the student ID. Yes, your student ID. These 8 students will be also be counted in the calculation in my grading calculations, right? Okay. Anyway, let's just start. Okay, 3, 2, 1. Okay, the double integral. I hope 2 minutes, around 2 minutes. Okay with you? Okay. Yeah, later. I've shown in the middle of the class before this feedback. Not sure why you're not paying attention. Okay, 1 minute. Okay. Okay, 2 students. perhaps you could use your student ID or name. Okay, next one. Get ready. Okay, 3, 2, 1, let's start. Okay, find the average value. Suppose it's too short, right? The time. Well, let's say you could have a triangle. Yeah, I think this one too short. I'm sorry. Should be at least 3 minutes. 2 3 minutes. Okay, but I think you did good job. Okay. Yeah, you could use your name, okay, for the Ashley and Crook, or maybe student ID. Okay, last question. Yeah, giving you really long time, 5 minutes. So remember, you don't need to write the pi. Okay, you just write the number, and if it's in a fraction, write in a fraction. Okay. Okay, we still have 1 minute 40 seconds. Okay, 25 seconds. Okay, 3, 2, 1. Yeah, 9/4. Okay, congratulations, you in the game. Again, now this will be the end of our lecture. So I hope you get. Uh, if you feel confused, let me know, okay? And we can still review the materials. We still have much time for before final exam, okay? And anyway, the QR code. If you need the QR code, if you haven't, scan. So if you don't have any questions, I think you could leave the meeting room and